Hi, my name is Steven and this is the first of the GAME2020 lectures. The target audience for this talk are the game developers at Digital Arts and Entertainment, and I will be talking about the dual quaternions. So we have a little overview of what we'll handle in this lecture, and it's quite a lot of stuff, so let's get right to it. Most of you will know the dual quaternions from their applications in blend skinning. So what we have here on the left hand side is your normal so-called linear blend skinning, where you use matrices to represent your bone transformations. You then transform your vertex with each of those bones and you weight the resulting positions. This has some problems, and one of those problems is known as the candy wrapping artifact. And this is why dual quaternions got introduced into the game developer scene, because you can actually blend the dual quaternion where you can't blend the matrix. And so what you get is this nice volume preserving animation. Another application that you might have seen dual quaternions being used is for mechanics, robotics, kinematics, and so on, where you can use dual quaternions to simplify what is a rather tedious matrix equation into something that is much more readable and understandable. Dual quaternions are often explained or introduced, at least, using either this rather big multiplication table or by simply telling you that it is the tensor product between the quaternions and the dual numbers. Neither of these introductions are very insightful, I think, and so we will try to do something a little bit more creative today. If you find videos talking about quaternions that mention four-dimensional spheres, then you probably should run. Alright, so why are the dual quaternions so hard to understand? Well, the main reason I think is because they are only half of the picture. So the dual quaternions are what is called the even subalgebra of a geometric algebra called PGA. This is not the first time I'm talking about PGA. We gave a lecture in 2019 at SIGGRAPH about geometric algebra for computer graphics. And in that lecture, we showed how PGA is an exceptionally elegant replacement for linear algebra and vector and matrix algebra that we typically use for a whole wide range of tasks that the graphics developer has to deal with. We did so by introducing three new special numbers called the geometric numbers, which were these non-real numbers that square to -1, +1, or 0. Then using those numbers, we defined our geometric primitives, points, lines, planes, and we showed how they transformed. We got a lot of excellent responses on the SIGGRAPH course, but one point was considered quite controversial, and that is that the vectors in this algebra, the grade 1 elements, are actually planes, and the grade 3 elements are points. And so why was that considered so controversial? Well, I think it has to do with the way we are used to formalizing geometry. So formalizing geometry, that means you have these nice drawings in the sand that allow you to build a very good looking and straight building. And you want to pass that knowledge on, you want to formalize it, you want to make sure that your neighbors can also use the hard work you did. And so the typical way to do that is we define an object representation, we figure out how are we going to write our points down and lines and so on. Then we figure out how they transform, and then we figure out how to compose those transformations. Now, when we first started doing this, like Euclid's first attempt was rather unsuccessful, but when we first started doing this, we used vectors in R3. And so we just went, okay, let's use vectors to write down directions and points, and then we can make lines and planes from those directions and points, which gives us an object representation, a very simple, easy to understand object representation. So how do they transform? Well, again, for translations, we can simply use vectors, and then to do rotations, it's a tiny little bit more complicated. You have to use 3x3 matrices, but it's still fine. And the composition, well, a full transformation is, of course, full transformation A is the combination of a matrix A and a translation vector A. And if you want to compose transformation A and transformation B, then you have to multiply both matrices and use this formula to calculate your updated translation vector. So this is a workable solution, and we actually use this solution still today for some applications. But there are also some problems with it. And so what are the problems? Well, one of the problems is that our representation isn't unique. So if I give you one of these vectors with 3 numbers in there, then it could be a direction or it could be a point. And you can't really tell. So you have this one element and there's actually 2 meanings. And this is sort of problematic because on this other side, when we have these transformations that are represented with matrices, these are not covariant. So you need 2 elements to do one type of transformation. You want to transform a point, you're going to need a matrix M, but if you want to transform a normal vector, which is a direction, then you're going to need some other matrix, the adjugate matrix. And in computer graphics, we often use the inverse transpose, which isn't entirely correct. Another problem is that not all elements are included. So lines and planes are, as well as our transformations, are really combinations of our elements. And you need a matrix and a vector, and here you need a point and a direction and so on. So there's no natural representation for these elements. You have to code all of that up yourself. And then the last problem is that this bag of matrices really is too big. And we are using 3x3 matrices, which are 9 numbers, to represent 3 degrees of freedom for the rotations that we're using them for. So that's really quite a few numbers too much. So we can do better actually, and in computer graphics we usually use R4 instead of R3. And this gives us a number of advantages. For starters, you can now use the extra coefficient to distinguish between your directions and your points. But much more importantly, your translations become matrices also. And the benefit there is that your composition rule becomes very simple now. So you just multiply 2 matrices to do the composition. So that is a lot better already, but there's actually some problems that are still there. So even though we can now distinguish the direction that we use for a normal vector or the vector that we use for a point, we still need these 2 different matrices to transform them. So here we still have this same problem that not everything transforms in the same way. There are still elements that are not included. So there's still no natural representation for a line. You still have to use a point and a direction, and you have to use a point and a direction to represent a plane. You actually can do planes, but most often I don't see people do that. So there's still elements that are not included in the algebra. And in the SIGGRAPH, of course, we actually showed that there is an alternative to using R4, which is using R301, PGA. And what that gives you is you get all of the elements are included. So you have natural representations for planes, lines, and points, both Euclidean and infinite versions. You also get all of the transformations, not just the rotations and the translations, but you get reflections and point reflections and so on. And you still get that very simple composition rule. So that looks great. We have all of the elements included, everything transforms covariantly, and it is just the right size. And it is actually easy to work this out if you go from the assumption that your grade 1 elements are planes. But this is exactly the point that was considered to be so controversial. Because why are you doing things upside down, and why must vectors be planes, and can't we just invent some new product so that we can keep calling the grade 1 elements points? Well, I don't really think we're doing things upside down. And so we're actually going to spend some time in this lecture to clear that up. And how are we going to do that? Well, since I really want to start by saying grade 1 elements are planes, but that's controversial, we're not going to do that. So we're not going to start with the object representation. Now, this might be a little bit of a problem, because if you have no objects, then we won't really know how to transform them, which in turn is also a bit of a problem, because then we can't think about composition. So it seems like we're in sort of a deadlock, but there's actually a way out. So if you have this page with things drawn on it, and you have to rotate it, but you're not allowed to measure or do anything to your objects or describe your objects, then you need to get creative. So what we'll do instead is we will do this. We will simply turn the page. And that is actually quite interesting, because when you transform the space, you actually get free covariance. All of the elements that you drew on the page, they will obviously also turn when you turn the page. And so that is a big win. And this idea of transforming the space is what we will go with. So we will formalize geometry in a different way, and we will start with the transformations. We will simply describe the transformations of space, start from an empty bag, and see where we get. So the transformations that we are interested in specifically are those that don't stretch, steer, or bend the space. They're also called the Euclidean or distance-preserving transformations. If you want to write that down a little bit more formally, you have some objects, points, lines, or elephants, then some distance function between them, and then we are looking for all of the maps F that when you apply them to both objects, that the distance function will still give you the same result. These symmetries are also called isometries. And we will start by looking at the projective plane and try to fill our bag with all of the isometries of the projective plane. That bag, by the way, is called E2, the Euclidean group in 2 dimensions. All right, so our bag is empty, and the first transformation that is obviously not going to change distances is the identity map. So we put the identity map in our bag, and we move on to the second obvious one, which is the reflection. So when you say symmetry, it's probably the first thing you think about. So when we reflect the plane, then yes, indeed, all of the distances stay the same. We also note that when you reflect the plane, that all of the plane changes. All of the points go to a different position, except for those that are on the mirror. We also note that reflections don't preserve orientation, so they flip things inside out, which is also called an opposite symmetry. They're also discrete symmetries, so they're not continuous. You can't do a little bit of reflection. There is no reflection close to the identity map. And then the last thing we notice is if you repeat the same reflection twice, then you restore the plane to the original position. We put all of the reflections in our bag, which already had the identity, and we move on to the next one that everybody is quite familiar with, which is the rotation. So again, let's look at this symmetry specifically. So it rotates the entire plane except for the pivot point. It does preserve handedness, it preserves orientation, which is also called a direct symmetry, and they are continuous. So there is always a rotation very close to the identity map. Good, we put our rotations also in the bag and move on to the next one, the translation. Same exercise. The translation obviously moves the entire plane, except for, well, there's actually something it doesn't move, but I haven't rendered it yet, so let me show you. So the point at infinity. So each rotation keeps one point at infinity invariant. They also don't flip things inside out, so they preserve handedness, orientation, and are called direct symmetries, and they're continuous symmetries, as there is always a translation close to the identity. Are we ready if we put the translations in our bag? Well, no, there are still other isometries. One example here is this footstep reflection, which is called a glide reflection or a transflection, and it's not yet in our bag, but it's also rather obviously a combination of a translation and a reflection. And that leads us actually to the following. Instead of enumerating the remaining isometries, let us just add composition to the bag. So we will add all of the functions that we don't have yet by simply adding any combination of translations, rotations, and reflections. Obviously, when you have a function A that keeps distances the same, you have a function B that keeps distances the same, and you apply one after the other, then you get this other function that also keeps distances the same. A question we can now ask is, are we ready? Do we now have all of the possible isometries in the plane? And we actually do, and it's actually quite easy to show you why. So imagine that we have these two random triangles. They could be anywhere in the plane, so there's no condition on where they are when we begin. Well, we can now always find the isometry between any two of these triangles by starting with the translation that moves the first point of the triangle to its destination position. You then follow up with a rotation, which moves the second point in place, and then you might be done, but in this case we have an extra reflection that we need to construct the entire isometry that takes any triangle to any other triangle. And so this is in fact the list of all possible isometries. We had no requirements on the triangle, so whenever distances on this triangle are preserved, they are preserved for the entire plane, so we now know that we have all of those possible maps. But we actually have a new question, a new thing to wonder about. Since we've added some of these isometries by composing others, we could ask, are we really sure that the ones we already had, that they were fundamental, that they were the fundamental building blocks? And to find that out, we're going to look at the composition of two reflections. So the first thing, and we already noticed this when we looked at the reflection, when you have the same mirror twice, because there's actually two mirrors here, and the blue triangle is the original triangle. So when we have the same mirror twice, then you get the identity map. Okay, so when it's not the same mirror, but they intersect, then what you actually get is a rotation. So we are doing two reflections here, the blue one to the light blue one over the blue axis, and then the purple axis, the light blue one gets reflected onto the purple one. And so what we see is if two mirrors intersect, then what you get as a resulting isometry is in fact a rotation. And it is a rotation that has this center point as the pivot point, and it also has twice the angle of the mirrors. So if the mirrors are at 90 degrees, then we have rotated 180 degrees. And if the mirrors are at 180 degrees, then we've rotated a full 360 degrees. So rotations were no fundamental isometry. You can build rotations by using two reflections. And actually, if the mirrors don't intersect, what you get is a translation. So translations too can actually be built by simply using two reflections. And what this actually tells us is that the reflection is the absolute basic building block for these Euclidean distance preserving transformations. And what it also gives us is a new question. So we figured out that by composing reflections, we can do zero reflections, which is obviously the identity. We can do one, which is obviously just a reflection, and two reflections become rotations or translations. Three reflections are those glide reflections, the footstep ones that we saw, and also rotor reflections. But what happens with 4? What happens with 5? And how far does it go? So let's look at that next. To see that, I have this new visualization, which is sort of an attempt at displaying where space goes. So if we have the identity map, everything is red, which sort of means everything stays in place. If we do just one reflection, then we get a reflection. And here it's sort of difficult to display a reflection. It should be instant, but it's slowed down very much. And so you can sort of see where all of the points go. And you can see that all of the points move except for those that are on the mirror. So we already know when we do two reflections, we get this rotation. And when they intersect, it's a rotation, and when they are parallel, it actually becomes a translation. And here you can also see that this is a very smooth transition when you go from translations to rotations. There is no point where it snaps over or anything like that. All right, so we also know when we do three reflections, this is a rotor reflection, and if I were to make some of these parallel, then what we get is this footstep glide reflection. Good, so what happens when we do 4 reflections? And this is of course the interesting case, because we don't get anything new anymore. So when we do 4 reflections, we actually just get a rotation, or we get a translation. Just the same as we did when we had 2 reflections, which means that we can actually write 4 reflections as 2 reflections. We could have 2 planes here that go through this red dot, that is the pivot point, with exactly the right angle to make this rotation or translation. And that's interesting because it also means we're done. If you have 5 reflections, then you could rewrite the first 4 as 2, so you just get 3 reflections again. And if you have 6 reflections, you can rewrite it as 2 again, and so on. And so we get closure. There are never going to be combinations of more reflections than this because they will already be in the bag. This is actually a very famous theorem. It was originally introduced by Elie Cartan and then later on generalized by Dieudonné, and it says that every orthogonal transformation of an n-dimensional symmetric bilinear space can be described as the composition of at most n reflections. Good. We now know that we're done. We have closure on our bag. We have all of the possible isometries of the Euclidean plane. So we have the identity, we have all of our reflections A, B, C, and then when you multiply two of them, A, B, C, A, B, A, C, B, C, then you get rotations and translations, and then you also have roto-glide reflections. And so there's nothing more here. This full bag, all of the isometries of the plane, again, is called the Euclidean group. Now, many times we're not interested in all of the isometries of the plane, especially the reflections and the roto and glide reflections. We're often not interested in. They flip things inside out, and many times we don't care about those transformations. And so it is actually possible to leave them out. If we remove the reflections and the roto-glide reflections from the bag, then we actually get another bag, which is called the special Euclidean group, and it just has the identity, the rotations, and the translations. And you should note that it is also closed under multiplication, because if you have a product of an even number of reflections, it will always be even. So 4 simplified to 2, and 6 will simplify to 2, and 8 will simplify to 2, and so on. Now, it is still quite a big bag. What I mean by that is it has all of the rotations for all of the points. So if you take a point, let's say the origin, then you have 1 degree around the origin will be in here, 2 degrees rotation around the origin will be in there, and so on. So all of those rotations, and then you take another point and you get again all of those rotations, and they are all in this bag. Now, you could say, sure, we've taken out the reflections, but we sort of still have compositions in here, right? Because if I have the element that rotates 2 degrees and I have the element that rotates 1 degree, then obviously if I square the 1 degree, I will get that 2 degree element. So if AB rotates 1 degree, then AB squared rotates 2 degrees, and AB to the power of x rotates x degrees. And so you can actually make an even smaller bag, and you do it using the exponential map, and it really only has 1 rotation for every point. And this bag is called the Lie algebra. And actually in PGA, these will be the pure bivectors. And if you consider the dual quaternions, they are the pure dual quaternions and the imaginary numbers as opposed to the complex numbers of the pure imaginary quaternions, if you look at the quaternions. All right, time for a recap. So we made this bag with all of the transformations. We are sure that we have all of the transformations. We have closure on the bag, so we have identity, reflections, rotations, translations, roto and glide reflections. We already know how to do composition, as we simply introduced it as normal multiplication, and now it is time to think about the objects. And to think about the objects, I actually have a similar visualization as we looked at earlier, where I can do any number of reflections, but this time in 3 dimensions. So if I don't do any reflections, then obviously I just get the identity and all of the points stay in the same place. When I do 1 reflection, what I get is all of the points move except for the points on the mirror. They stay in the same place. When you get 2 reflections, what you get is a rotation. So all of the points move except for the points that are on this intersection of the 2 reflection planes. When we do 3 reflections, what we actually get is a point reflection. So all of the space goes to the other side of the point, and the only point that stays in place is this one particular point. What happens when you do 4 reflections? Well, that's sort of an interesting case. What you get is a screw motion, and you see here that all of the points move, so none of the points stay in the same place, but there is still a line that doesn't move, which is the axis that you're rotating around, and there's an associated line at infinity that also doesn't move. Now, what happens when we do 5 reflections? Well, we simplify back to 3. So this is again to be expected by Cartan-Dieudonné. We use a 4-dimensional space to model 3D PGA, and so 4 reflections is the absolute maximum. When you do 5 reflections, it just simplifies again. But the point here is that if you have elements to represent all of these transformations, then they already have a very strong link with the geometry. When you have a reflection, it leaves one line in 2D or one plane in 3D invariant. And so we already have an element that really represents this line or this plane. And while there are many rotations that keep a point line invariant, we can easily pick the orthogonal one. And so this is what we do in PGA. We identify the geometry with the invariance of the symmetries. This creates a very elegant algebra. It is coordinate free, dimension independent, and the expressions are actually very easy to reason about. Right, we have still one question left to answer. So we get this nice algebra of symmetries. It has the identity, this is the 3D version, and it has the identity, the reflections, rotations, translations, point reflections, and screws. And then some of these elements are being used, the transformation are being used to also represent a geometry. So when you have a mirror representing a reflection, it also represents a plane. And when you have 2 mirrors that cut orthogonally, it also represents a line. And when you have 3 mirrors that cut orthogonally, it also represents a point. But we still have to answer the question, how do we transform the elements? The group composition operator is the ordinary product, but how do we transform the elements? Well, we actually do it the same, using the same trick as we did before. If we have this red line that we need to rotate, then we simply first rotate our space. We write down our line and we rotate our space back. And this gives you this sandwich product. And the trick here is that the sandwich product can transform anything in the middle, because it's really transforming the space before and transforming the space after. And that is actually easiest to understand once you realize that any element you write here actually is also the composition of a number of reflections. So if we have a line here, this is just the same as saying there is a rotation here, because it's the product of 2 intersecting planes, excuse me. Good. Now, the next question is, of course, how are we going to actually do calculations with this? And so this is, of course, just PGA again, but what we really need conceptually is some sort of special number, some type of number that's not a real number, and that squares to identity. So it is a mirror. We need a mirror. And then even when we have these numbers that we could use to represent mirrors, then we need some other type of special number, because we also need this mirror at infinity, this plane at infinity. And obviously, if you reflect in a mirror at infinity, you should expect to get 0. There is no coming back from that reflection. It is not invertible. And so, of course, these are those geometric numbers. And so really what we do is we write down our reflections using linear combinations of 3 Euclidean mirrors, called E1, E2, and E3, and 1 mirror at infinity. And what it boils down to is you can just take a linear equation that describes an arbitrary plane in 3 dimensions and write it very simply as a vector in PGA, a grade 1 element in PGA. So let's do a little test in 2 dimensions, just to make sure that these lines, these linear equations, now also represent reflections, because of course we need them to do that. So we take an example line, x plus y plus 1 equals 0, which is then converted, like I mentioned before, to E1 plus E2 plus E0, and it is this red line that we have here. Then we take a second line, which is x equals 0, which is just E1. It's the blue line we have here. And what we do is we calculate, we sandwich the red line using the blue line. We expect this to reflect the red line in the blue line. So let's do it real quickly here. So we have E1 times E1, which is of course just the same mirror twice. So that's the identity. We have E1 times E2, which is the E1,2 rotation. And we have E1 times E0, which is the E1,0 rotation, or the minus E01 rotation. And then we multiply with E1 to the right. We get 1 times E1. We get E1,2 times E1 is minus E2, because we have to do one swap. And we get minus E011, which is just minus E0. And this indeed is that equation of this pink line. So you can use linear equations to represent mirrors, and you can use the geometric product to do your function composition, and that actually is all we need to know, because the rotations and translations are just multiple reflections, and the same for point reflections, and the same for screw motions. And at the same token, we also get this automatic representation for our lines and our points, which then turn out to be Plugger coordinates and homogeneous points. So really all you need to know to get all of this working is you need to have these geometric numbers, 3 of them squared to plus 1, 1 squared to 0. You need to remember your anti-commutativity, and then it's just the ordinary product and using linear equations. Now, of course, it is good to work through the algebra and figure out what happens to each of the coefficients once. But then you sort of need a better way to think about it. You need a way to visualize PGA. And so what I'm talking about is this is what you would be used to for working with vectors. So you have vectors pointing at points, and then you can visualize things like the sum of two vectors or the scalar product and so on. You actually will find people using a similar type of view to show how things go on, what goes on in Clifford algebras, and then they'll do things like use this exact same image to illustrate the wedge product, which I don't think is a great idea. So we'll do something different today, and we'll do something that is a little bit more ambitious. We want to have a visualization for PGA that allows us to visualize all of these products, all of these elements, and all of these transformations in such a way that you can actually reason with it. And so how are we going to do that? Well, let's start with the elements. For lines, we'll just use lines, and for points, we will just use points. So that's not very spectacular, but it is a very natural representation. Now, of course, we also want to show rotations and translations, and so we're actually going to use a slightly modified version of this, which is this. So we will still use points for points, but we will remember that they are bivectors, which means that they are the product of two vectors, which means that they are the product of two lines, and they are pure bivectors, so they don't have a scalar part, so it also means they are the product of two orthogonal lines. And then the rotations, we already know they are the product of two reflections that have an intersection, which will be the pivot point, and they will generate a rotation with twice the angle between those lines. For translations, we use parallel lines, and we know that they will generate a translation with twice the distance between these lines. Now, the first thing to note when you look at this is that there is a certain degree of freedom. So lines and reflections, they have this one-on-one relationship, but for all of the others, you can actually do this without changing the meaning. So if we turn it a little bit, then this is still the product of two orthogonal lines. This is still the product of two lines intersecting at the same point with the same angle between them. These still have the same distance between them. So doing this really doesn't change anything. And this is actually the degree of freedom that you can use to understand what goes on when you start looking at the products of geometric algebra. And that's what we'll do next, and we will start with the geometric product between 2 points in 2D PGA. So we have our 2 points here displayed with this orthogonal factorization. If you look at the algebraic version of what is going on, then you might be able to recognize this expression here as being a translator. But let's show an easier way to figure out what's going on. So we use our degree of freedom, and what we will do, what the geometric product does by anti-commutativity, is it will actually try to find identical mirrors. And when it does, when you get these two identical mirrors, that's twice the same mirror, that's the identity map, and it vanishes. And so what we are left over with when we take the geometric product between 2 points in 2D PGA is two lines through these points that represent the translation. These are parallel lines, and they represent twice the translation between the 2 points. That's the geometric product. It looks for equal reflections, and as soon as it finds them, it eliminates these identical mirrors. Good. We have some more products, of course, in PGA, so let's look at another one, the inner product. So we are going to look at the inner product between a point and a line, and you could again try to figure out what goes on by looking at the algebra, but we again have an easier way to do it. So where the geometric product eliminated identical mirrors, the dot product will actually isolate orthogonal ones. So it'll turn things around just like the geometric product in order to find this orthogonal reflection. And all of the other ones vanish. And so when you take the inner product between a point and a line in 2D PGA, you get a new line that is orthogonal to the original line and through the point. For the regressive product or the joint, we again have a similar rule. So for the geometric product, we have eliminate identical reflections, the inner product retain or isolate orthogonal reflections, and the join retains identical reflections. So it basically does the same thing as we did in our first exercise, but now instead of throwing the identical mirrors away, it retains these identical mirrors. And indeed, we have produced the line that joins our 2 points. Then we have one product left over, which is the meat or the outer product. And what the meat or the outer product will do actually is it will rotate things around to find specifically the orthogonal reflection that has the same invariant. Good. Using these very simple rules, you can actually get a good idea of how the operations in PGA work, and also the more complex ones. So let's look at some of those next. Let's start with the projection operator. So we have our point A and our line B, and what we want to do is we want to project point A onto line B, and we want to also project line B onto point A. If you look at the SIG graph course, you will see that there are 2 formulas to do this, and they both start with B dot A. So let us first visualize B dot A, which was isolating the orthogonal reflections. And we remember, if we take the inner product between a point and a line, then we get this new line through the point orthogonal to the original line. If we now multiply this new red line B dot A with the original line B, then we just get the composition of 2 orthogonal reflections, which is a point. And it is exactly the point A projected onto the line B. If instead we take B dot A and we multiply it with this orthogonal decomposition of point A, by multiplying it with A again, then we remember that the geometric product removes identical mirrors, and the only one that's left over is this green one, which is indeed line B projected onto point A. What we can also visualize is Cartan-Dieudonné. So I told you before that when you have 4 reflections that in the plane, that it simplifies to 2, and that it's impossible to have 4 reflections. So let's see how that works. So we have 2 rotations here. One rotation is around this pivot point with twice the angle between the 2 lines, and the other one is around this pivot point. So what we can now do is we can actually get one of these mirrors to go through this point, and then we do the same thing on the other side. And as soon as we do, we get these identical mirrors in the middle, and they collapse, and what we are left with is our new rotation. This will be its center point, and it will have twice the angle between these 2. Now, of course, you say, if this thing wants to... Oh, okay. So, the next one. We're doing the same thing, looking at Cartan-Dieudonné, but this time we have a rotation and a translation. So, the translation, you say that it has no intersection point, but we remember if we rotate around infinity, then we can actually get that to work. So, we can still do as we did before and simply find the mirror that collapses and discover that we will get a new rotation, which is our original rotation just translated actually. Then there is one last scenario in 2D that I want to show you, because there is one extra trick you need to know. What if we have the reflection of a point? So I have line A and I sandwich this point with line A. Now you say, okay, I can't really rotate anything here because these are 2 mirrors and I can't rotate the mirror. And you'd be correct, but what we can do is we can actually use associativity. So instead of rotating this point in the middle, we could actually say, oh, you know what, we consider the first A and B, which has this rotation point, and we can just put our brackets around that and rotate that one. And then we can do the same thing here, and we can say, oh, the A that's on the right and the C, I'm going to rotate those together. And what happens is you get the eliminating mirrors in the middle, and you will find this point, which is exactly the point you were looking for reflected over this original axis. And everything also just works the same in 3D. So here is that first exercise again, where we take the geometric product between 2 points. We rotate our points around, try to find identical mirrors, and as soon as we do, they collapse. And what we find is that, just like in 2D, when you take the geometric product between 2 points, you get a translation between the points. And there is one more that I want to show you, and that's this one, because we'll need it for the dual quaternions in a little bit. So we are going to consider the geometric product between 2 lines that are in the same plane. So there are 2 scenarios. We have 2 lines in the same plane that intersect, and we have 2 lines in the same plane that are parallel. And this is again the same exercise. We simply take the geometric product, so we are finding where these mirrors get to be the same, and then you see when the lines intersected, then what we get is a rotation, and when the lines were parallel, we would have gotten a translation. Good, so that should hopefully give you a good way to think about the operations in PGA, and we are now ready to talk about the dual quaternions again. And what that means is we will start a brutal violation of this beautiful algebra that we've been talking about. What do we mean with brutal violation? Well, for starters, the dual quaternions don't do reflections or point reflections, so we take them out of the bag. Now, of course, you'll say, okay, if you take those out of the bag, you now no longer have that natural representation for planes and points. And that is true. But there is a patch. Remember from the start that we used to represent lines as a direction and a point, and that is because lines have 3 coefficients that transform like points and 3 that transform like planes, and so you can actually use lines to stand in for the points and the planes that you have thrown away. Now, of course, you say, well, this is still a pretty algebra. I mean, you can still see that these guys are 2 reflections, and you can see that there's this one guy with 4 reflections. This is definitely not something that you would carve in a bridge. Everybody would say this is much too simple. That's just vandalism. But there's a patch for that too. So you can actually do some renaming, and you have to do it really clever. So you rename E12, E31, and E23 with I, J, and K, so you can't see it's 2 reflections anymore. And then some of the others that were 2 reflections, you're going to rename them with epsilon I, epsilon J, and epsilon K. And then to really confuse everybody, you take the 4 reflections and you rename it as just being epsilon. And so this is totally bridge-worthy. This is what I call bridgeable. You can carve this and it'll have people confused for a very, very, very long time. Now, luckily for you, you can also just unpatch that. And here I think the minus signs and the bases are actually correct. So what do? You get something in on this dual quaternion basis, and you simply rename it back to the reflection basis so you can see the internal structure again. And if you have to create any dual quaternions and so on, you simply use PGA lines. You use the product of 2 lines that intersect to create a rotation. You use the product of 2 lines that are parallel to create a translation. And you can just call it a dual quaternion after you do the renaming again. And it's actually not just the dual quaternions that follow the same type of mindset. So if we restrict ourselves to planes through the origin, then we actually get the quaternions. And if you do only lines through the origin in 2D, you actually get the complex numbers. Good. Time for a recap, I'd say. So several of these important symmetry groups actually have direct Clifford representations. So the grading that you get in this group because of Cartan-Dieudonné is exactly the grading that you get in a Grassmann algebra. And each of these representations also has a natural invariant association with the geometry. So we have 2D and 3D PGA, which are the Euclidean group in 2 and 3 dimensions, which are all of the reflections, rotations, translations, rotor reflections, and screws. And the associated geometry are the planes, the lines, and the points left invariant by these transformations. And if you consider only the direct or orientation preserving transformations, then you have the special Euclidean group in 2 and 3 dimensions, which we classically call the planar quaternions and the dual quaternions. Now, these are general planes anywhere in space. If you restrict yourself to the origin, then you get a very similar picture. So you have the geometric algebra R2 and the geometric algebra R3, which represent the orthogonal group in 2 and 3 dimensions, which are all the reflections and the rotations that leave the origin invariant. So they are the planes and the lines through the origin and the origin point itself. And the even subalgebras are the special orthogonal group in 2 and 3 dimensions called the complex numbers or the quaternions. Now, this idea actually extends even past this. So, for example, you could have R13, which is the space-time algebra, where you get all combinations of reflections, rotations, translations, and boosts, and where the even subalgebra represents the Lorentz group, and you have R31 and R41, which are 2D and 3D CGA, where you have the conformal transformations, and I actually have a little visualization of that one to close things off. So what happens in these conformal geometric algebras? You still get this buildup of a combination of reflections. So if you have no reflections, you still get the identity map. This is 2D conformal geometric algebra, and what is different there is when you have one reflection, this is not just a line reflection, but it can also be a circle. This is called an inversion. So all of the space moves to the other side just like it does with a line, and what you keep invariant is a circle. If you intersect a circle and a line or a circle and a circle, if you apply two of these isometries, then what you get is a point pair. All of space moves except for 2 points that stay in the same place. And then you, of course, also have a representation for the point in CGA. And then the same thing in 3 dimensions, where, again, 0 reflections gives you the identity, 1 reflection gives you a sphere or a plane. When you do 2 reflections in spheres, what you get is a circle. So this is actually all of space rotating around this one circle that stays in the same place. And if the circle has an infinite radius, then it is actually a line, and you get all your Euclidean transformations again. And in 3 dimensions, you also get the point pair and the point. And then I have one last slide, which is just an advertising slide. There is a very efficient production-ready PGA implementation available by Jeremy Ong. It is called the Klein library, and it is very pretty, and absolutely, if you want to use PGA today for your gaming applications, it's definitely the place to be. All right, thank you.